Welcome to Electrodes and Potentiometry. So potentiometry is the use of electrodes to measure voltages that provide chemical information. Now we have electrodes that respond selectively to specific analytes in solution or in the gas phase. And these tend to be about the size of a pen, just like a pH electrode. We also have some ion-sensing field effect transistors that are tenths of a millimeter across, and these can be inserted into blood vessels to perform in situ analyte measurements. So an electroactive species is a species that can donate or accept electrons at an electrode. And if we have an electroactive species, we can then turn our unknown solution into a half cell by inserting an electrode, such as a platinum wire, that can transfer electrons to or from the analyte. And this electrode is then the indicator electrode. That is, it responds to the analyte. It indicates how much analyte we have present. Now we can connect this half cell to another half cell using a salt bridge. And this second half cell is then the reference electrode. That is, it has a constant potential. And so the reference electrode is then everything you see here in this dashed box. It contains the silver electrode, it contains the silver chloride there, and it contains a saturated potassium chloride solution. Then it contains a salt bridge that will allow ions to flow to connect with our other solution, our analyte solution. So suppose we want to measure the relative amounts of iron 2 and iron 3 in solution. So we've got this solution here, we have some iron 2 in there, we've got some iron 3, and we want to know how much of each one we have, or the relative amounts of those two. Now, we can make a galvanic cell by inserting a platinum electrode over here, and a reference electrode, which is then again everything in this box. And the two half reactions are then shown here. We have our iron 3 being reduced to iron 2, with a potential there of 0.771 volts. And then we have our silver chloride solid being reduced to solid silver and a chloride ion, and our cell potential there is 0.222 volts. Now remember that we could have written the second reaction differently, that is, without the chlorides here and there, but the potential of the complete cell would be the same. Now we can write expressions for the electrode potentials. For the cathode, we then have E plus is equal to 0.771 volts minus 0.05916 volts times log of the ratio between the iron 2 concentration and the iron 3 concentration. And then for our E minus, we have 0.222 volts minus 0.05916 volts times log of the chloride ion concentration. And the complete cell potential is then E plus minus E minus. And again, I'm denoting this with E sub cell, whereas Harris denotes this with just a capital E. And that value then is the E plus expression minus the E minus expression. But in this case, the chloride ion concentration here is fixed by the solubility of our potassium chloride, and thus the cell potential only depends upon the ratio between our iron 2 and iron 3 concentrations. Now, the left half cell plus the salt bridge is the reference electrode, and this then has a fixed potential. Now, the platinum wire in the right half cell over here is our indicator electrode, and changes in the cell potential are coming entirely from the right half cell, that is, only from over here, as our ratio between our iron 2 and iron 3 concentrations change. That is, because we have a saturated potassium chloride solution here, then the concentration of the chloride is not changing here, and that means that everything within this box is essentially constant, at least as far as our cell potential is concerned. We may be changing the mass of potassium chloride that we have down here, or the mass of our silver chloride that we have there, but because those are both solids, we are not changing their activities. and thus we're not changing the cell potential of our reference electrode. Now the portion of the figure enclosed in the dashed line on the previous slide can be constructed in a relatively small package that can then be easily dipped into our analyte solution. Now the one shown below here is what we call a double junction electrode that minimizes contact between the analyte and the potassium chloride in our inner electrode. That is, we have our inner electrode here, and we have an outer compartment here, and each of these have a porous plug that allow ions to flow, and so basically this outer compartment is then the salt bridge to allow ions to flow back and forth across each of the porous plugs, and thus complete our circuit from our inner electrode here around to our platinum electrode. So this reference electrode is much easier to use than a standard hydrogen electrode, because the standard hydrogen electrode requires hydrogen gas at 1 bar and a clean platinum surface for catalyzing that reaction. The platinum surface is easily poisoned by many solutions and will thus be quickly deactivated. And so this is a relatively high maintenance reference electrode, the standard hydrogen electrode that is, because we have to bubble our hydrogen gas through, we've got to keep it at a pressure of 1 bar, and we have to keep our platinum surface clean, and this is going to be relatively difficult for us to do, whereas if we compare this with the silver chloride electrode that we had just shown, that one is relatively easy. We just need to keep plenty of silver chloride around, we need to keep plenty of solid silver in our electrode, which is easy to do, and we need to keep plenty of potassium chloride solid around, and that will keep the chloride concentration fixed in solution. Now the standard reduction potential for our silver chloride to silver electrode is plus 0.222 volts at 25 degrees C if the chloride activity is 1. But the activity of chloride in the saturated potassium chloride solution isn't 1. The reduction potential of the electrode is in fact plus 0.197 volts instead, because we have a different concentration of our chloride ions here. And that means that where we have an E0 of plus 0.222 volts, for our saturated potassium chloride electrode, we have a cell potential of 0.197 volts. Now over time, the porous plugs in the reference electrode can become clogged and cause a sluggish, unstable response voltage. That is, if these porous plugs, if some of the channels in those porous plugs become clogged, then we're going to have a more difficult time getting ions to pass back and forth through those plugs, and that then will lead to a delay in our voltage difference between our inner electrode and our indicator electrode. Now we can construct a different reference electrode based on this reaction, where we have silver chloride. Now bear in mind this is silver 1 chloride, because the silver 1 ion is a polyatomic ion with 2 silver atoms, where each one has a charge of 1 plus, but the overall polyatomic ion has a charge of 2 plus. And that then, because it has a charge of 2 plus, our chloride there has to have, since it has a charge of 1 minus, we need to have 2 chloride ions paired with it. So we have our mercury 1 chloride going to mercury liquid. This is mercury in its elemental state. Remember, mercury is a liquid at room temperature. And then we have our chloride ions. Now, the E0 here is plus 0.268 volts. But if we have instead a saturated potassium chloride solution fixing our chloride ion concentration, then the cell potential there is plus 0.241 volts. And this electrode is a special electrode because this one turns out to be relatively easy for us to use, and this is what we call the Calomel electrode. And that's because the mercury 1 chloride here is called Calomel, and if the potassium chloride is saturated, then we have what we call a saturated Calomel electrode, which we symbolize with a capital SCE. Now note that if some liquid evaporates from the electrode, then the chloride ion concentration doesn't change because we have a saturated solution with potassium chloride. If we've evaporated some of the water, then we simply precipitate out some more of our potassium chloride. Likewise, if the solution gains a little bit of water, The concentration of our chloride ion will still not change because we will simply dissolve a little bit more of our potassium chloride. Now there are two types of indicator electrodes that we are going to look at. The first is metal electrodes that develop a potential in response to a redox reaction at the surface of the metal. And the second type is ion-selective electrodes that develop a potential due to a binding of one type of ion to a membrane. Now, these electrodes do not work via a redox process. So common metal indicator electrodes are platinum, because it's often inert, gold, because it's usually even more inert, and carbon of various forms, like graphite, because rates of many redox reactions are high on the carbon surface. That is, the carbon effectively acts as a good catalyst for a lot of different reactions. Now, a metal electrode works best if its surface is large and clean. And to clean it, first we want to dip it in hot 8 molar nitric acid. Bear in mind you want to keep this in a fume hood, and then you want to rinse it well with deionized water. Now we can use a silver electrode paired with a reference electrode to measure the silver ion concentration. And the reaction at the silver electrode then is the reduction of our silver ions to metallic silver, and we have E0 plus there of plus 0.799 volts. And note that this silver electrode is this electrode here, the one on the right side here. On the left side, in this case, we have a double junction saturated Calomel electrode for our reference electrode. So the reaction at the Calomel electrode is that reaction that we've seen earlier. We are reducing our mercury 1 chloride here to mercury, and we have the chloride ions left over. And remember that E minus there was plus 0.241 volts. So the potential of the reference electrode is plus 0.241 volts. And remember that this is E minus, not E naught minus, because the activity of the chloride ion is not 1. In order for us to have E naught minus, we need to have the activity of our chloride ion to be 1. But that's going to be harder for us to fix the activity of chloride ions at 1 than it is to simply saturate the solution and use this other value instead. Now the Nernst equation for the complete cell then looks like this. Remember, we have the cell potential E is equal to E plus minus E minus. And so E plus is then this first term here. The E minus there is this positive 0.241 volts. And now we can combine together our plus 0.799 and our 0.241 volts. And that then gives us 0.558 volts plus 0.05916 volts times the logarithm, base 10 here, of the silver ion concentration. Now suppose that we have a 100 milliliter solution containing a 0.1 molar sodium chloride, and that was titrated with 0.1 molar silver nitrate, and the voltage of our cell was monitored. So what reaction are we looking at in the titration? Well, the reaction that we're looking at is the reaction between our silver ions and our chloride ions to then form our solid silver chloride, and this is then a precipitation reaction. So the equivalence volume is the point at which we have added equal quantities of our silver ion and our chloride ion. And thus, the equivalence volume would be 100 milliliters. So let's say we want to calculate the voltage after the addition of 65.0 milliliters, and then again after adding 135 milliliters of our silver nitrate. Well, first, let's look at the 65 milliliters. At 65 milliliters of silver nitrate added, then 65% of our chloride ion has precipitated, and 35% of it remains in solution. And so we can then say that our chloride ion concentration is the fraction remaining, that's our 0.350, times the initial chloride ion concentration of 0.100 molar, and then times a dilution factor, because we started out with a volume of 100 milliliters, and if we've now added 65 milliliters of our silver nitrate here, then our total solution volume is going to be 165 milliliters. And when we work out the math, that ends up giving us a value of 0.0212 molar. Now we can then use the KSP expression to find the silver ion concentration. So we know KSP is equal to the silver ion concentration times the chloride ion concentration. And so if we know KSP is then 1.8 times 10 to the minus 10, and we know the chloride ion concentration from the last slide was then 0.0212, then we get a silver ion concentration of 8.5 times 10 to the minus 9 molar. And we can now find the cell voltage. So remember we had this expression earlier, and now we can go ahead and plug in for our silver ion concentration. We can plug in our 8.5 times 10 to the minus 9, and that then gives us a value of plus 0.081 volts. So now let's look at when we've added 135 milliliters of our silver nitrate. At this point, we've now reacted all of our chloride ions, and I have all here in quotes because we haven't actually reacted away all of our chloride, but we've reacted away virtually all of it. In any case, we have an excess of 35 milliliters of our silver ions, and the silver ion concentration then is our 35 milliliters converted here to liters that we have extra multiplied by the concentration of our silver nitrate solution divided by our total volume. We started with 100 milliliters and now we've added another 135 milliliters, so our total volume is then 235 milliliters. And when we work out the math, that then gives us a value of 0.0149 molar for our silver ion concentration. And we can now find our cell voltage, plug in our 0.0149 here for our silver ion concentration, and that gives us a value of plus 0.450 volts. Now the figure to the right here shows the titration curve. And note that anytime we have P of X, just like with pH, this is equal to minus log base 10 of the X concentration. So we can plug anything we want in here for X. If we have pH, then pH is minus log base 10 of the hydrogen ion concentration. pOH is minus log base 10 of the hydroxide ion concentration, and so on. So we can plug in a P value for our silver ion concentration, and that then would be PAG. And we can then replace the log term in our Nernst equation here, this term, with our PAG, the power of silver ions. Now because of the solubility equilibrium, our silver electrode is also a halide electrode, if we have solid silver halide present. Now in the case of silver chloride, we have our KSP expression here. We can rearrange that to solve for our silver ion concentration. And that means that in our expression for the cell potential here, we can replace our silver ion concentration with KSP divided by our chloride ion concentration from here. Now let's define a junction potential. A junction potential is the voltage difference that forms at the junction between two different solutions. Now usually junction potentials are just a few millivolts, and these form at either end of a salt bridge. And we normally don't know the value of the junction potential, and so the accuracy of our potentiometric measurement is limited. That is, the cell potential that we actually observe is equal to the cell potential itself plus the potential of our junction potential. So let's examine a silver chloride solution that's in contact with deionized water. So we have over here our sodium chloride solution, and on this right side of our interface we have the deionized water. Now, the sodium ions and the chloride ions diffuse across this junction from left to right into the deionized water. But the chloride ions diffuse faster than the sodium ions do. That is, the chloride ions have a higher mobility. And that then gives rise to a region here where we have a region that is rich in chloride ions because they have outpaced our sodium ions, and then a region behind that that is rich in our sodium ions because the chloride ions have already diffused out of that region. And thus, a region enriched in our chloride ions forms in front, with a region enriched in sodium ions, or depleted in chloride ions, that forms behind it. And therefore, we're going to have an electrical potential difference between our sodium chloride solution and are water phases. Now the charge buildup opposes the chloride ion movement and accelerates the sodium ion movement. Because of course, the chloride ions are going to be repelled from this region, and they will be attracted to that region of positive charge, and the sodium ions will be attracted to the region of negative charge, where we have a buildup of chloride ions, and they will be repelled from the region that has a buildup of positive charges. Now, ion-selective electrodes respond to just a single ion, and these don't involve a redox reaction. Instead, a potential develops at a thin membrane that binds only the ion of interest, or at least ideally only the ion of interest. Now let's examine the liquid-based ion-selective electrode that we have over here to the right. The ion-selective membrane is a hydrophobic organic polymer containing an ion exchanger and perhaps a ligand, L here, that binds with the analyte cation, which we're symbolizing here with a C+. Now we have here a container containing our analyte solution down here. We have an external reference electrode here, and then we have an internal reference electrode in there. And this whole portion here is the ion-selective electrode. Inside, in contact with that internal reference electrode, we have this filling solution. And then we have an ion-selective membrane right down here. Now at that ion-selective membrane, inside we have that filling solution. The membrane itself is this region here. And then the outer solution, this is our analyte solution that we have out here, is then represented down here. Now in this case, our L, our ligand, is valinomycin. Our cation of interest is potassium ion. And in this case, our R- is this ion here. So note that our R- ion here is only contained within our ion-selective membrane. And inside, in our inner filling solution, inside our electrode, we have some cations here, in this case our potassium ions, there, and they are typically bound near this B- in this case. And then out here, we then have our potassium ions bound to our, in this case, A-, some other counter ion. Now the filling solution inside the electrode then contains our C+, in this case our potassium ions, and its counter ion B-. And the analyte solution surrounding the outside of our electrode, that's down here, contains our analyte, C+, again in this case that's potassium ion, and a counter ion A-, and it may contain some other ions as well. Now ideally, it doesn't matter what our A and our B and what the other ions are, but in practice it may. So note that in this case, two reference electrodes are necessary. We have this inner reference electrode inside our ion-selective electrode, and then we have another reference electrode outside. That's our external reference electrode, and that one then goes directly into our analyte solution. Now the voltage difference between the reference electrodes, between our inner reference electrode and our external reference electrode, indicates a difference in the activity of our potassium ions, or our C+ ions, whatever that happens to be, in the internal filling solution and in the external analyte solution. That is, what is the difference in activity between this solution in here and this solution out here? And we can then use a calibration curve to tell us the activity of our cation in the analyte solution out there. That is, we calibrate the potential differences between our two electrodes for a variety of concentrations that we already know, so we use the standards, and then we can compare those standards against our analyte solution to determine our concentration of our cation in the analyte. So let's look at pH measurement using a glass electrode. This is the typical electrode that we use to measure pH. Now the glass electrode we use to measure pH is the most common ion-selective electrode. Because of course, to measure pH, we simply need to find out the concentration of the hydrogen ion. So that is just an ion-selective electrode. Now usually we use a combination electrode to measure pH. And this electrode has both glass and reference electrodes in one compact body. And so you can see a schematic over here. You can see that we have our two leads here. Those will then go to our pH meter. one of them goes down the inside here, and that goes down, and on the outside of that is then this silver chloride paste. We have, for our negative electrode, we have that going around, and it's wrapped around this inner glass tube. And again, on that, we also have a silver chloride paste. In the inner electrode, we then have some liquid inside in our inner reference electrode, and that's going to go all the way down here, and we're going to have this glass membrane. This is going to be a rather thin bulb of glass down at the bottom. In the outer electrode, this solution will be an aqueous solution that's saturated with silver chloride and with potassium chloride. And note here that we have a little hole here, and this has a porous plug in it to allow slow drainage of our electrolyte out of our electrode. And note here that we have down at the bottom some solid silver chloride and some solid potassium chloride. Note that inside our inner electrode in this glass bulb at the bottom, we have a 0.1 molar hydrochloric acid solution that's saturated with silver chloride. Now we can write a line diagram of this cell, and it's going to be really quite long. So we have in our outer reference electrode, we have our solid silver, and then we have a phase boundary there to then the solid silver chloride, and then another phase boundary to our aqueous chloride ions. We then have a salt bridge to then, this is outside our glass electrode. So we have the hydrogen ion concentration outside our glass electrode. And then a phase boundary, that's the surface of our glass membrane. And then the inside of our glass electrode is then the hydrogen ion concentration inside that electrode, inside our glass bulb at the bottom. And also in there, we have then this bit. Now all of this is our inner reference electrode. And in that same aqueous solution that we have here for our hydrogen ions, we also then have our chloride ions, and then we have our solid silver chloride and our solid silver. And so note that on this side, we have this outer reference electrode, and on this side, the inner reference electrode, we have exactly the same electrode, we've just basically flipped it around. Now the reference electrode on the left side of the line diagram, over here, this is our outer reference electrode, is that coiled silver chloride electrode. And the reference electrode on the right side, this inner reference electrode, was our straight silver chloride electrode. And the reference electrodes measure the voltage difference across our glass membrane. That is, across this membrane. This line then represents our glass membrane, because this is outside our glass electrode and this is inside our glass electrode. And the salt bridge here was then our porous plug, allowing some ions to flow into or out of our outer reference electrode to then our solution outside of our glass electrode. So remember that the silicate lattice in glass has an irregular structure. That is, it's an amorphous solid. And so you can see down here, we don't have a nice crystalline lattice structure where all of our atoms are in a regular place within the lattice. We have this irregular structure, and that then allows for some of our cations here to penetrate into the lattice, at least to some degree. Now, cations with a +1 charge can move slowly through our lattice, and the surfaces of the lattice that are exposed to water become hydrated and form hydrated gel regions. So if we have an overall glass thickness of 0.1 millimeters, a tenth of a millimeter, which is pretty thin for glass, it's going to then be fairly fragile, so you need to be careful with your pH meter. On the outer surface and on the inner surface, or rather, on the inner surface and the outer surface, we have these two regions that are shown in blue here and there, and these are roughly 10 nanometers wide. We have that hydrated gel layer. And in these regions, we have exchange sites that are occupied by hydrogen ions and sodium ions. And then in between there, we have this dry glass layer, and all of our sites are occupied by sodium ions. And then again on the other side, we have the exchange sites that are occupied by our hydrogen ions and our sodium ions. Now these hydrated gel regions need to stay wet, and this is why you have to keep your pH probe, or at least that glass portion of it, wet all the time. You never want to allow it to dry out, because then these regions here will dry out, and those hydrogen ions will no longer be able to penetrate into the glass in that region. Now the metal ions in that hydrated gel region can migrate out of the glass and into the solution, and then the hydrogen ions can then migrate into the membrane to replace those metal ions. And this is then an ion exchange reaction. And note that a pH electrode responds selectively to hydrogen ions because only the hydrogen ion will bind significantly to our hydrated gel layer. That is, other ions don't bind significantly to our hydrated gel layer. Now, in order to perform an electrical measurement, there must be some current flow, although it may be very small. And thus, we must have some ions moving across the glass membrane. Now, the hydrogen ion does not move through the membrane, but sodium ions can move slowly through. Now, note that the resistance of our membrane is generally around 10 to the 8th ohms. And the potential difference of our cell then depends upon the chloride ion concentration in each electrode compartment and the hydrogen ion concentration on each side of our glass membrane. Now, the chloride ion concentration in each compartment is fixed due to the solubility of our potassium chloride. As long as we have some solid potassium chloride around, then the concentrations in each of those compartments will be the same for our chloride ion. And the hydrogen ion concentration on the inside of the glass membrane is fixed because we have a 0.1 molar solution. And thus, the only remaining variable is our hydrogen ion concentration outside the glass membrane. Now we must modify the Nernst equation slightly to describe the response of a real pH electrode. That is, we have our cell potential for the outside of the electrode. That is, we have our cell potential is equal to some constant plus beta times 0.05916 times log of the activity of the hydrogen ion concentration. And note that minus log of the activity of the hydrogen ion concentration is pH, and so we're going to have to change this sign here from a positive to a negative, and then we can take this log of the activity of hydrogen ion concentration and turn that into then the pH. And we can then calibrate the electrode, and in that case we're then measuring what this B, or beta here, needs to be. So let's talk about where some errors in pH measurements can come from. First, they can come from the standards. The standards that we use to calibrate our electrode generally have an uncertainty of plus or minus 0.01 pH units. Also, some error can come from our junction potential. Remember that a junction potential forms at the porous plug in our electrode, and if the ionic composition, that is the dissolved ions and their concentrations of our analyte solution, are different from the standard buffer that we use to calibrate, then the junction potential will change. And this will occur even if the pH of the analyte is equal to that of the buffer. Now the uncertainty from the junction potential is about 0.01 pH units as well. Furthermore, we can have junction potential drift. Most electrodes have a silver chloride reference electrode that is saturated in potassium chloride. Now, the potassium chloride can precipitate in that porous plug. And if the analyte solution contains a reducing agent, then silver solid can also precipitate in the plug. And both of these will change the junction potential and thus our pH measurement. Now we can also have a sodium error. When the hydrogen ion concentration is very low and the sodium ion concentration is very high, the electrode responds to the sodium ion and the apparent pH is lower than the true pH. And this is sometimes called an alkaline error. We can also then have an acid error. That is, in strong acid, the measured pH is higher than the true pH. And this effect may be because the glass is saturated with hydrogen ions and thus cannot be further protonated. We also need to bear in mind the equilibration time. It takes roughly 30 seconds for the electrode to equilibrate with a solution that is well buffered. Now, a solution that is poorly buffered, as would be the case near the equivalence point of a titration, requires significantly longer to equilibrate. And last, we have hydration of glass. If the electrode has been allowed to dry, it will require a few hours of soaking to rehydrate before it will correctly respond to the hydrogen ion concentration. Also, the electrode must be calibrated at the same temperature at which the measurements will be made. If the temperature is changing, then we will have an error in our pH measurement. Also, we need to bear in mind the cleaning of the electrode. If the electrode has been exposed to a hydrophobic liquid, it must then be cleaned with a solvent that will dissolve the hydrophobic layer and then conditioned well in an aqueous solution. If this is not done, then the apparent pH of a solution can drift for hours while the electrode equilibrates with an aqueous solution. Now, the first two errors, the buffer uncertainty and the junction potential, limit the accuracy of our pH measurement to plus or minus 0.02 pH units. And we can't ever eliminate those two errors. Now, differences in pH between two solutions may be accurate to plus or minus 0.002 pH units. And note that plus or minus 0.02 pH units is an uncertainty of plus or minus 5% in our activity of the hydrogen ion concentration.